Right. Hi, everybody. Welcome to today's presentation, Below the Surface, Demystifying Water Pollutants. My name is Ava Swift, and I'm an AmeriCorps member serving with Conservation Nebraska's Common Ground program. Conservation Nebraska's mission is to protect our state's natural legacy by educating the public, supporting communities, and increasing civic engagement. We do this through locally led education efforts and community engagement projects that address conservation concerns across Nebraska. Before we begin, I have a few quick housekeeping items to go over. Your cameras will remain off and you'll be muted throughout the presentation. Please type any questions you have in the chat or in the Q&A section and we'll answer them during or after the presentation. This presentation will be recorded and uploaded to Conservation Nebraska's YouTube page within the next couple of weeks. If you miss any part of tonight's presentation, want to revisit something, or would like to share it with others, you can find it there. After the presentation, we'll launch a very brief survey that should take less than a minute to complete. This survey helps support programming like this, so we really appreciate you taking the time to fill it out. If anyone in attendance is interested in speaking with a Conservation Nebraska member about conservation issues in Nebraska or learning more about what we do, I'll also put our email in the chat. Tonight, we're excited to welcome Dana Richter-Egger from the University of Nebraska at Omaha. He'll be speaking with us about what is going into our water and what concerns we should take seriously. Dr. Dana Richter-Egger is a faculty member in the Department of Chemistry at the University of Nebraska Omaha, where he's also the director of the Math Science Learning Center. He teaches courses in general chemistry and environmental chemistry with research focused on soil and water quality, lead contamination in Omaha, and STEM education. His background in analytical chemistry and environmental studies makes him a valuable resource for helping the public better understand water quality, environmental safety, and how to navigate science through concern. With that, I will turn it over to Dr. Richter-Egger.
Great to be here. Thank you for the kind introduction. I want to make sure before we get too far, if we could get some of you on Zoom in the chat, just drop us a note if you can hear, if the volume sounds all right, and if you can see my first slide, the title slide, Below the Surface, Demystifying Water Pollutants. I don't want you to miss that. So while we do that, oh, can I use that? I can't use that.
We have to click back on the presentation.
Oh, now I can. Okay, awesome. Thank you. Are we good on Zoom? We get some indications. Looks good.
I think so, yeah.
Outstanding. So, a few things to talk about today, all around water. There's so much. It was difficult to choose what to include in a presentation like this, but I'll do my best, and I hope that all of us learn something through the process. Can we go back to that other screen? Yeah, okay. So my name is Dr. Richter-Egger. In addition to the things that Ava mentioned, I wanted to share, I've been at UNO since 2001 after earning my PhD in chemistry. This is a kind of a photo montage of me. On the left, you've got a pH probe out in a creek. This is Glacier Creek near the large cottonwoods in that upper central photo. And we've been out there collecting water samples, looking at water quality, water composition, particularly as it relates to that preserved prairie and its relationship to the surrounding agriculture. I grew up on a farm, so you got a tractor, you got lightning bolt in the upper right. You can't grow up on a farm, I don't think, and not be paying attention to the weather. And in the center of the screen, there's an instrument called the ICP-MS. It's just one of many tools that we use in the chemistry department that I use for water quality. On the right, looks like a chemical. That's a chemical. The main reason it's there, it reminds me of the things that I love best about science is discovery. And that's what drives me and my work. And then, as Ava mentioned, I'm also a director of the Math Science Learning Center. So we provide all kinds of support, academic support for our university students. Today, we're thinking about water as the universal solvent. And this is a quote from the U.S. Geological Survey that we need to take that statement, water is the universal solvent, with a grain of salt in it. So chemists are only funny periodically. Apparently, geologists are funny periodically as well. But of course, water doesn't universally dissolve everything. But it dissolves more substances than anything else, and the earth is covered with it, and we're full of it, and all of this matters in terms of our health and our surroundings. And so it's really, really, really important. If you want a dark example, think about a cave. Cave systems exist because water dissolved all of that stuff. That's how it got to be there. Thought, a lot of different ways to jump into this. So 3 cities and 3 stories. I have a feeling you probably know 2 of these cities and maybe not the 3rd city. Anybody? I won't even try to pronounce the city in California. Does that not ring a bell? The folks online, I can't tell if you're raising your hand or not, but this is a community in California. About 20 years ago, their city council was considering banning the chemical dihydrogen monoxide. And dihydrogen monoxide is I don't know what that sounds like to other people. To a chemist, it sounds odd because I never use that chemical name, because what I'm really referring to is water. And that city council, like I say, about 20 years ago, was considering banning dihydrogen monoxide because someone brought to their attention that it's used in the manufacture of all kinds of things, and it can kill us, and all right. And true story, the city council was considering that. If you're wondering, can water kill us? I can attest to that. I've almost drowned twice in my life. Both times as a teenager, just feeling more brave probably than I needed to on occasions when I don't swim very well. But that's one story in one community. I hope most of you, sadly, are familiar with Flint, Michigan, and the water crisis that occurred there. Some slightly more recently than the story from that California community. And I listed Omaha, Nebraska. Oftentimes, if I talk about Flint, particularly if I'm talking with an audience of students or others, no, Omaha is not Flint. No, our city council didn't consider something like that. But it's up to us to make these decisions. And some of these decisions happen at city council levels. Some of these decisions happen at the water treatment level. The only reason that we know about Flint, Michigan is because of somebody's decision. And I'm not going to go into, what their intent was necessarily. All of this has been fleshed out in a variety of different settings, but ultimately it was human decisions. And my position is Omaha and any other community, we're like one decision away from being as well known as Flint, right? And there's nothing particularly special about Omaha, but we're run by people as well. So paying attention to these things matters. All kinds of headlines in the news. This one's from, again, a number of years ago, antidepressants make for sad fish. I believe this is a perch. And I did not rotate the photo. That's the fish just kind of hanging out in a vertical orientation. That's not what they usually do. I guess maybe it's not. I don't know. Because it's now, this was in a setting where, I believe it was Prozac, gets eliminated from our bodies after we use it, goes into the wastewater, gets into the rivers, and the fish were behaving differently. And that was the headline from that particular case. Somewhat more recently, this is one that came across my email, probably this past spring, because I didn't see it immediately. EPA approves pesticides with PFAS for food use. I was like, what? Like, this is just not, it doesn't make sense to me. So I had to go do some digging, and my opinion, I think the headline is both accurate and not quite what I would choose as a headline. And I can get into more here about that in a little bit. But there's all manner of, I'm going to call them sensational headlines that we get bombarded with every day. Things that cause cancer in our tap water, flesh-eating bacteria and toxic sludge, prescription drugs, contraceptives, deadly rocket fuel found in everyday water, bottled water, that is. Part of the purpose as I understood it for this presentation, like the title suggests, is demystifying some of this stuff. So we have all of this kind of coming at us, and what do we need to take away from that? On the flip side, Lauren Isley once said, if there's magic on this planet, it's contained in water. And it makes me think about water as a universal solvent. It makes me think about water as kind of the substance of life, water as a source of our health, our food. Whether you think that's magical or not, it's pretty cool what water does and how it does it, particularly given how simple water is. As again, I said earlier, I'm a chemist, and so I'm thinking about some of these things a little bit differently. Water, the stuff that we drink. So I say, I'm going to go get some water. And I go over and I get a bottle and I go to the tap. It's easy to think about, oh, well, that's H2O. Well, it's a lot more than H2O. And it's not as scary as lions and tigers and bears. But when you, again, whether it's a bottle or from the tap, you've got something and you can rightly look at that and call that stuff water. But it's not only H2O. There's minerals, there's runoff. That's the worst part about when I reflect on almost drowning twice. Like I'm in one of Nebraska has many great man-made lakes for flood control and erosion prevention, and I know whatever other reasons we've built these things. But you know, I know where I grew up on a farm. I know where the cows are. I know what cows do, and I know what leaves. So I'm swimming in this stuff almost dry. Anyway, like runoff has a lot of things in it. Pesticides, the plastics, the pharmaceuticals, the PFAS, the bacteria, the heavy metals, household chemicals, all of these sorts of things. But before we get too carried away and I get too excited, let's pause with minerals for a moment. I would ask, when you were a child, did your mother, father, somebody who cared about you say something along the lines of, hey, you know, little person, don't use the hair dryer or the radio or the curling iron while you're in the bathtub, right? We were probably told this, and for good reason. But it's not because of the H2O, it's not because of water itself, it's because of the minerals that are in the water. And this stuff occurs naturally. Again, I grew up on a farm. We know well water has abundant minerals that are dissolved in it. It's the minerals that conduct that electricity. If we had pure H2O and we had a bathtub full of it, we don't have to worry about that electrical hazard. There's properties of everyday properties of water that we take for granted that deserve a deeper look. By the way, if you thought maybe, hey, I've got ultra pure water and I'm going to fill my bathtub with it, don't get in the bathtub because it's going to dissolve stuff from your bathtub. It's going to dissolve stuff from your skin. And before you can blink, it's going to be conducting electricity again. These are all things that we look at the university, both in kind of the research laboratory, but also with undergraduate students working on these projects. When we're doing that, one of the tools that we're using is ion chromatography. And I wanted to include this so that, again, demystifying some of what's in our water, right? So this is an animation of the components of this instrument that we use. There's liquids, there's a pump, there's a sample, there's an injection valve. When we analyze a sample, we might take a small, only like 1 milliliter. Can you click an arrow for me, Ava? There we go. And we'll draw up 1 milliliter of that sample into the loop. That loop rotates, and so we're using a mechanical valve, and then that sample travels with the eluent to the column, and all of those minerals that are in the water and all of the other substances that are in the water travel through that column, but they travel through that column at different speeds. What that looks like then on the kind of the readout end of things is a graph like this. On the horizontal axis is time, and on the vertical axis is something called resistivity. This has been sped up. The horizontal axis is in minutes, and obviously this is going faster than minutes. But this is one of the sort of tools that both we use at the university, but they're going to use this same exact tool. My understanding is in every drinking water and wastewater treatment facility, this is one of those tools that is really, really widely used because it really gives us a lot of great information about many of the components that are in drinking water, including things like sodium, ammonium, potassium, calcium, and magnesium. Those components, we know what they are because they have different residence times on that column. They take a different amount of time to leave that column, and that helps us to know what they are. You might guess that the larger peaks, there's more of them, the smaller peaks, there is less of them. That's all true as well. This sort of technology is, in a sense, not super dissimilar from the sort of thing that you might find in your water softener at home, but we're using it in a different application. So we'll look for those minerals. I'm going to go forward first. We'll look for these others: fluoride, chloride, nitrate, phosphate, and sulfate. We'll look for all of those common things. And when we do, we're not actually detecting, in a sense, we're not detecting chloride, we're not detecting fluoride, we're not detecting nitrate. The detector is kind of dumb, if you will. The only reason I know it's chloride is because something hit the detector, and I only know it's chloride because of the time that it's hit the detector. And so one of the things that I wanted to emphasize is, as whether it's your public water utility, somebody at the university, a private test that you ask for, oftentimes what's going to be measured is going to be measured indirectly. And we're going to measure something else on that. And then in this case, that's peak area. And so we're going to measure the area under that curve. My chemistry students all talk about the calculus that they might also be studying because that helps us to do that. But thankfully, the software does it for us. So we can make one measurement, and we use what's called a standard curve to relate what we're actually measuring to what we actually want to know. So if we're monitoring for fluoride in this case, we've got a peak area. We use that calibration curve, and then we can calculate the concentration. There's uncertainty in the peak area, there's uncertainty in that concentration. All of that depends on the technique, the quality of the sample, the quality of the analyst doing the work. And we're going to repeat that process for each of those components in drinking water. When you get a result, if whether, again, that's from, if you're looking at the report from your public water utility or a sample that you send off somewhere, that's part of what's happening in the background when they're doing that analysis. Ava, you're going to let me know if there's questions online?
Yep.
I get going really fast. Are there questions? Okay, I can pause for questions at any point.
We don't have any right now.
All right. So then, yeah, you have to go back so I can put it in. Sorry.
There you go.
So other things that we do that I've been involved with at the university, this includes service learning projects where we take university students. It's one of the few occasions where chemistry professors get to go on field trips. And so this is some example data from university students. We went out to the wildlife safari park that's off the Ashland exit of Interstate 80, just from where I'm at on the other side of the Platte River. And there's a couple different creeks, there's a couple different ponds in the Wildlife Safari Park. Beautiful place. If you haven't been, you should go check it out. We collected water samples from all these. All these are from within the Wildlife Safari Park. The reason I wanted to share it here is that even in that, I'm not the geologist, but the geology is not identical throughout the park. But this is a pretty small area of Nebraska. This is, I think, like 100 acres, something like that. I wanted to bring this to you to show you the variability, in this case, in terms of water hardness. And so we've measured, these students have measured calcium carbonate. They've also measured nitrate. And what I wanted you to observe is the variability in these things. Pelican Creek, forget which one. Wolf Creek, I believe, feeds into Pelican Creek. And then this pond is an isolated body of water. But the amount of water hardness varies considerably, even within a single creek. This is surface water. It's not been treated. We're not planning to drink it either, by the way. We call this the foamy sample. I'm not drinking foamy water, right? But it's a good example of the sort of variability that you might see. You had a question.
What is water hardness?
So my apologies. I should have said that first. Water hardness, and that's why you got these pictures also on the screen. So upper right, shower head not in super great shape. You see on what used to be all chrome, you see some white chalky looking deposits. You see some brown rusty looking deposits. Both of those are hard water deposits. Hard water hardness officially is measured as grams. That's why that's listed this way. Grams of calcium carbonate. Calcium carbonate is not itself water hardness. It's a component of hard water. The other significant components of water hardness in this area, in addition to the calcium, would be magnesium and iron. All three of those are, you would say, marginally soluble in water. And when the water evaporates, it leaves those minerals behind. Because they don't dissolve very well, they start to build up. And so you'll see the little water spots, maybe on your shower door or on drinking glasses in the kitchen. And they're really difficult to remove because they form that solid material on there. It doesn't look great. Eventually, it's going to start to plug those holes in the shower valve or in your dishwasher or in your washing machine. So it's hard water is chemically, again, those particularly the calcium and magnesium and iron ions. If you wanted to be broader about it, it's cations that are it's not poly. They're not singly charged. They would be doubly or triply charged. So things like sodium and potassium are also in drinking water, but they don't form the scale. That's what's in the picture on the left. This is a sliced view of a water pipe. And it's got all of these rings. It looks like tree rings, right? But these rings are hard water deposits that are gradually building up over time. Reduces the water flow of the pipe, not very helpful for your house. Eventually, it might get closed off completely. There's also some beneficial sides to that I want to get to in just a moment. But water hardness is usually thought of as a problem, usually thought of as something that we want to combat. And so the normal solution for that would be a water softener. Water softeners that's kind of their singular job is to remove, they're not going to remove all of it, but they'll remove maybe 90, 95, 98, some large majority of the calcium, the magnesium, the iron ions, so that your pipes don't get that much buildup and your shower heads and your dishwashers don't get that much buildup. The other thing that happens is it interferes with the soaps and the detergents that we use. And so when you're showering, when you're washing dishes, laundry, all of those sorts of things, you'll need more of those materials, those detergents and soaps, if you have hard water relative if you have soft water. On Zoom, we have a question.
Yes. Jess asked, how often do wastewater treatment plants have to change their cleaning and formula process to accommodate for changing contaminants? Or do they?
That's a fantastic question. That's not my area of expertise, but I'm confident that the right answer would be continuously. And I say that because the number of new contaminants continues to increase every day. And so I know, and that's a really broad statement, that they're always monitoring, they're always watching for those things. If the question is more about the, the mechanical swapping out of parts, I couldn't speak to that. The longevity of a particular filter or a particular process, there's going to be schedules for those sorts of things so that they continue to function properly. But it's a fantastic question, because all of that matters greatly.
You might be getting to this, but for the water softener, is that like a filter, like a strainer straining out those? Or is it a chemical that's breaking it down?
So so how water softeners work is pretty fascinating. I'm gonna go back to this schematic diagram from the instrument that we're using here. So in this separation column that's on the right of the figure, I usually describe it this way, that inside there, we put fancy sand. Fancy sand that's a loaded word, right? But I say fancy sand because water can flow through sand and water flows through this. You can imagine, nowadays we have all these smartphones, and so just keep pinch zooming, right? On a grain of sand, pinch zoom, pinch zoom, pinch zoom. We'll keep zooming in until we get to something like an atomic level and we can see individual atoms. What you'd observe in here, you're asking the right question, but the answer is relatively different, right? Rather than a screen that keeps bugs out or in your dryer that collects the lint, it's not a physical process. It's not about size. It's not about filtration. It's about adsorption. And so these ions, so hard water ions, right? The calcium and magnesium, they're in the water. They're going to be flowing through that column. But as they flow through that column, they'll get stuck. We know that opposites do what? Opposites attract. Okay. So the fancy sand is fancy in a very particular way so that it has an attraction for those calcium ions and those magnesium ions and the iron ions. There's others, but those are the main ones that occur naturally in our drinking water. There's an attraction for those things. And they just get, it's not magnetic, it's not Velcro, but it's kind of like that. You think about a process where there's an attraction, but it's also possible to overcome that attraction. And so you got your water softener, you get it set up, you get it all plumbed, and it's ready to go, and it's ready to start adsorbing all of those calcium ions. So the water flows through, and the calcium and magnesium get stuck behind. Eventually, the material, the solid material that's in there, all of the attractive sites, they're all occupied. So you might think about it like a hotel, right? Like once all the rooms are full, then what happens to the calcium? It passes straight through, and your water softener is not going to work anymore, which is why every so often your water softener goes through a recharge cycle. Okay, so that recharge cycle, and what do you have to add to your water softener? Big bags of plain old salt, sodium chloride. Those, and it's the sodium that's the important part. And we're not using a little bit of sodium, we're using a lot. Like think about the bags of sodium that go in your water softener. All those sodium ions, they don't have as strong of an attraction for those sites on that solid material, but they have some attraction. And they have enough attraction, especially when you put them in the quantities that we're doing. Think about like I don't know what, I'm just using random numbers, really. Let's say there's 1,000 sodium ions for every attractive site where there was a calcium ion. After 1,000 knocks into the door, eventually that calcium, I personify it, right? But it wasn't paying attention, and there's a sodium that come in and took its place. Well, now the calcium's back in the water. Sites are still all occupied. That calcium gets flushed out. That regeneration cycle one of the things that happens, there's some water that goes down the drain. All the calcium goes down the drain. All the magnesium goes down the drain. All the iron goes down the drain. All of those sites eventually get filled up with sodium ions because of the overwhelming majority of the sodium that's present. It's a numbers game, right? Calcium has a greater attraction, but sodium has there's way more sodium ions. So we play the probability game. Eventually we flush all the calcium off. That's the recharge cycle. Then we're back to the use cycle. It's loaded with sodium. And as our tap water flows through that column, then the sodium slowly get bumped off because the calcium has a greater attraction for that phase. And we retain the calcium again. One of the things you'll see, like if I go, can I have, and I'll go to the Zoom question real quick. Can you take me back to the screen?
Oh yeah, sorry, I didn't know.
No, you're good. I know we're doing multiple things with the tool there. So one of the things that you'll notice, so this water I can tell you is not particularly soft. The softer the water, all water that I see in this area has some sodium, and if it hasn't been through a softener, it's going to have some calcium, magnesium. If this was a soft water sample, these calcium and magnesium peaks would be almost invisible, and that sodium peak would be a lot larger because all of these ions had to get replaced with those ions. I have to do an exchange, right? I can't just remove, and it's an exchange process. What was the Zoom question?
Yeah. Janet asks, why do we need to know what's in the source water that feeds our personal or municipal drinking water systems?
Oh, wow. I mean, that's a great kind of follow-up to the other Zoom question. You know, that our municipal water utilities have to continually update their processes is because we're monitoring it, because we need to monitor it, because it continues to change. And water, one of my favorite things to say about water is it's probably the most recycled substance in the world. Like when I'm done with my water, where does it go? Well, it goes down the kitchen sink, it goes down the shower drain, the washing machine drain, other drains in the house, pipes, treatment plants. In the case of where we're at in Omaha, Nebraska, most of it ends up back in the river, and then it goes downstream. And the next utility, you know, Kansas City, St. Louis. I'm glad I don't live in New Orleans because who knows where that water has been. But the great thing about the water treatment plants, and right, that we're continuously monitoring and working with, they're selecting out the stuff we don't want, and they're selecting the stuff that we do want. Some of that has processes like similar to the water softening that I described. Follow-up questions to the water softening before I go forward, okay? So, what's next then? Before I leave hard water, I was just looking at MUD's website this morning. One of the things that our water utility is doing is working to remove lead service lines from Omaha. A whole lot of us right now get our drinking water through pipes made of lead. Most of us, rightly so, are scratching our heads a little bit, or we've heard about this before, and we scratched our heads, you know, the first time we heard about this. Why? What? Like, lead is not what we want in our water, right? Why would we do this? Well, there's mechanical reasons why lead was used. And there's a chemical reason why we thought it was okay to use. And most of us at this moment don't really need to be concerned about that lead service pipe. And the reason we don't really need to be concerned about that lead service pipe is twofold. One, our water people are making the right decisions. Part of those right decisions are the minerals that are being added to our drinking water after it's been purified. Those are the minerals that are creating some of this scale, some of this hard water deposit inside of our pipes. Too much of this is not good, but in Flint, Michigan, kind of the key decision that they made resulted in not enough of the mineral being added, and therefore when the water got to the pipes of the homeowner, these layers started dissolving. And if you've seen water, tap water from Flint, Michigan, from that crisis, it reminds me of the colors of these stripes. These stripes, these deposits were being dissolved. That's what was ending up in the water, and eventually enough of it dissolved that it began to expose that lead pipe. As long as these mineral layers are here, that lead pipe's not going to bother us at all. So there's some fantastic chemistry, but it's not only chemistry, because it's humans that are choosing what we're doing and what chemistry is going to be effective in there. So hard water, there's at least two sides to it, right? There's the unhelpful sides, but there's also the part that protects us. And so, and if you are inclined, there's some fantastic chemistry there. I wanted to pick on a few things that show up in our water. It's not quite a random collection, but this is just some of the things that I think more about than others. Because if you think about those headlines, right? Like there's so many headlines, and truly, I think, last time I looked at a water quality report, they're probably tracking, I don't know, upwards of 200, 300, 400 different substances in drinking water. Like it's a long list, and it's a growing list. So I just chose a few. Nitrate, lead, PFAS, microplastics, pharmaceuticals, fluoride. Some of these are like discrete substances. Microplastics and pharmaceuticals are categories, so I'm even mixed, and so is PFAS, a category. Which things ought we be paying attention to, and which things can we pay less attention to? That's a fantastic question. Any one of these things is important to pay attention to. So how do we sort through some of that? Well, I would, among other things, consider the risks, and I've not tried to be exhaustive. I've just listed a few things here for each of these things. But nitrates in drinking water can cause something called blue baby syndrome. There's too much nitrate in the drinking water, your body's going to absorb it. It's going to reduce your body's ability to transport oxygen. And if you've had, I'm trying to think of, one time I can think of this is like when I was a kid and I would just like wrap a string around the end of my finger and I'd watch my finger turn colors, right? Because that's what's going on with the chemistry of your blood and in your body. Don't gotta take the string off. Be careful, kids. But being able to transport oxygen around our body is really important, and nitrate reduces that. The current regulated limit for nitrate in drinking water is 10 parts per million. It's exactly what it sounds like. If you could see a nitrate and you could see water molecules, that means that if you have 1 million water molecules, anyway, grab me a little leeway. But essentially, it means if you had 1 million water molecules, you'd have 10 nitrate water molecules, right? More specifically, this is done by mass, but you can count them and get an idea, approximate idea. Yes?
That's the federal limit?
That's to the best of my knowledge, that's the EPA limit. Yes. And these change. So I don't remember when it changed. 20 years ago, I don't think that was the number, right? So we're also monitoring and getting a sense of, how there's a cost to if we have more than that in the water, how are we going to remove it? There's a cost to remove it. What's the benefit? It's not simply about chemistry. It's not simply about health. But what I wanted to do on here, again, some of the risks, blue baby syndrome, nitrates also associated with uranium mobilization. One of my favorite questions to ask. What do you think? Well, I might have had this conversation with Ava already. Diane, drinking water. Mm-hmm. More likely to see uranium in drinking water or lead in drinking water? Any guesses?
I'm guessing lead.
Right? I would have guessed lead too. My experience in analyzing, at this point, hundreds of area-wide drinking water samples, far more likely to observe uranium in water than lead. And I don't say that, it sounds scary, but it's not. It's way below, both of those things have regulated limits, by the way, lead and uranium. way below the regulated limits. Part of that is due to the tools that we have, things like, way back at the beginning, things like this instrument, right? I can find the kind of the chemical equivalent of the needle in the haystack. One needle in the haystack isn't gonna, right? But we can still observe it, we can still find it. That's different from, just because we found it doesn't mean that it's hazardous. So we've got to pay attention to what are the risks, we've got to pay attention to how much is there, and we've got to pay attention to, is that enough to cause the amount of risk that we're going to take some action to try to mitigate that risk. I would call your attention to the three numbers on the top numbers on the right. So we've got 10 ppm for nitrate, 15 ppb for lead, B as in boy for billion. 15 in a billion. There's 1,000 millions in a billion. Or if we're doing parts per billion, this is 1,000 times less concentrated, this lead limit, right? So what I can interpret from that is that lead is, I'm going to say, more important to be paying attention to because we're regulating it at 1,000 times smaller concentration than we are nitrate. And that's also consistent with my experience with these two things, right? If I had the choice, I'd drink the water with the nitrate, not with the lead. PFAS, increased cancer risk, lots of other things. Some of this is still emerging because PFAS hasn't been around as long as some of these others. The current, as far as I can tell, the current regulated limit for this in drinking water is 4 parts per trillion with a T. And so again, we've dropped by another fact. They don't all behave this way, but these three behave this way. PFAS is regulated at 1,000 times lower concentration than lead is regulated, which is 1,000 times lower than nitrate is regulated. That tells me, among other things, that the hazards of PFAS begin at much lower concentrations, or we wouldn't regulate them at that low of a concentration. There's too much cost in terms of the cost-benefit analysis kind of perspective to regulate something at a level that's not beneficial. So as you're thinking about what's in drinking water, that's those are two qualities that I would look at. What are the risks and what are the regulated limits? That's going to help. It's not going to be the definitive thing. And for some things that we might rightly be concerned about, there aren't yet currently established regulated limits. And there's other things in water, frankly, that we put there intentionally, like fluoride, because it helps to reduce tooth decay. So, but like anything, too much even of a good thing is still not a good thing. It still has a regulated limit. That's the maximum amount of fluoride that you want in your drinking water. Question from Zoom?
Yes. Janet said, what is the difference between naturally occurring nitrate from decaying non-chemically treated vegetation versus chemical fertilizer nitrates runoff from agriculture fields?
Great question. What's the difference between those sources of nitrates? From a chemical perspective, nothing. Like nitrate is nitrate sort of thing, right? It's all going to behave the same chemically. It's all going to have the same effect. Certainly there are multiple sources, and some of those are man-made. Some of those are naturally occurring. I think the other thing I would say about that is typically what I see in these conversations is that, you know, if whether it's nitrate or anything else, if it's the natural, there's this sense that if it's the naturally occurring amount, that may not be healthy, but it's not, that's the way we found it, right? And so we might rightly choose, well, I'm not going to put my well over there, I'm going to put my well over here. We would still use it as an informed sense, but what I think is behind that question is that yes, and many of these get well. So PFAS is entirely man-made. Microplastics are entirely man-made. Well, there may be some naturally. Most pharmaceuticals are man-made. Lead is not man-made, but we've certainly made it more abundant in the kind of environment where it's interacting with things, and right. So the man-made level of extent of these things is an important thing to consider. In the case of nitrates, like to the extent that there's a nitrate problem, it's my experience is it's always because of human development. Agriculture is part of that. Agriculture is not the only part of that. Yeah. Seeing if I can put some kind of a bow on this, sorting out what needs our attention. I talked about, looking at regulated limits, looking at the risks, other things that we want to be familiar with. Toxicity, the intrinsic health hazard of a substance, that's separate from the exposure, the amount of time that substance is encountered. So uranium is a great example. Uranium is in the soil, it's in Nebraska. I'm not only concerned with Nebraska, but I live in Nebraska, so I use Nebraska as the example, right? It's in the soil, it's in Nebraska. Nitrates, again, a lot of that is from agriculture. We've learned helps to mobilize the uranium. And so the toxicity in that example of uranium didn't change. Uranium is both radioactive, which is not good for us. It's also chemically toxic. You don't want the chemical parts of uranium either. There's no, to my knowledge, biological valuable amount of uranium in our diet. The toxicity didn't change. The toxicity of uranium is what the toxicity of or whatever the pollutant is, right? The contaminant, the mineral, whatever you're talking about. The toxicity is intrinsic quality of that material. The exposure is not an intrinsic property of that material. The exposure can change. Nitrate changed our exposure to uranium. If I drink a lot of water, I have greater exposure to what's in that water than if I drink a small amount of water. Our behavior helps to inform our level of exposure. The likelihood of, back here I talk about lead causing issues with brain development. Well, that's maybe not a good example. PFAS, increased cancer. You have cancer or you don't have cancer. Just because there's PFAS in water does not mean that you're going to get cancer. So you have to consider what's the probability, what's the likelihood at a given exposure for a given substance that a given outcome is going to occur. Those things are separate from the concentration. If the concentration goes up, there's the possibility that my exposure could go up. There's a possibility that that outcome could go up, but that's not the only factor. What's the severity of that outcome? We're talking about cancer or are we talking about fingernail fungus? Right? Like these outcomes aren't all equal. And what's the cost to either reduce or I won't say eliminate because that's just the wrong way to think about it. What's the cost to reduce our exposure or reduce the concentration of whatever that substance is? So we want to be familiar with those terms and the way those affect our health and which ones are in our control and which ones are not. It's a good opportunity, I think, to remind ourselves of the distinction between causation and correlation. And so I have here something completely unrelated. The sale of ice cream plotted as a function of month of the year versus the prevalence of forest fires on the same plot. And if you look at this and you look quickly at this, you're like, hey, these two things are tracking similarly. Hey, I could mistakenly say it looks like ice cream consumption is causing forest fires. Or maybe somebody says forest fires are causing ice cream consumption. I don't think either of those things are true. Doesn't make sense to me that either of those things would be true. They're clearly correlated, but Probably you agree. I don't know if you agree with me or not. My position would be that the one did neither of these caused the other one. And so when you're thinking about toxicity, exposure, likelihood, concentration, severity, cost, make sure that you're considering cause and effect as distinct from what's simply correlated. They're not the same thing. We talked a little bit about water treatment. You could spend, I could spend a whole semester, a whole course looking at water treatment. But what I wanted to, we talked some about water softeners, but I wanted to compare some of these different systems. So public water compared to our home filters, compared to water softeners, which is not a water filter, and compare that to reverse osmosis. Earlier, there was a question about water softeners, and does that thing is it like a filter? Is it like a net? There are things at home that function more potentially like a net, and that would be a home filter. Home filters there's some adsorption going on with home filters as well, but if you're talking about particulates and some of the larger things, maybe bacteria, there's some much more kind of net catching qualities to home filters. The water that's come to our home, I'm going to assume either was from a public water system that's both centralized and regulated, and so they've done a whole lot to the water. So it comes out of the tap, it looks like water, it smells like water, tastes like water. Most of us, even almost kind of by default these days, have home water filters in our refrigerator, right? Before I had one in my refrigerator, I had one on the tap. The reason that I bought one, the occasion when I bought the home filter, when I became a dad. And I was like, suddenly I'm like, I'm responsible for another human. And then it was multiple humans. And these are growing, developing humans. And I know even at that point that all of these things are way worse for human development than they are for human existence. And so that was a quick addition to our home, was that home filter. How much did it really change the quality of life for my little humans that aren't so little anymore? It's really difficult to know, but it gave me a lot of peace of mind. And I probably won't know the answer, but I know the answer. If I didn't do that, we were at greater risk for potentially greater exposure because of what may or may not happen to that water after it leaves wherever it was treated. It's not simply peace of mind, it is literal protection. And my wife reminds me, usually a few days before the little light on the refrigerator goes off, she's like, I don't think it's tasting right anymore, right? These filters are doing things, and some of it's just about taste, but they're doing real things. And I find personally real peace of mind in having that. I don't pass the laundry water or even my shower water through a filter like that. I've thought about it. Our skin's our biggest organ. Not so much worried about the washing machine, but the bathtub, the shower, that matters. Maybe not quite as much as the water that I put in my mouth, but it matters. So hopefully we've got people making good decisions at the public water level. We can make some choices as an end user about both kind of the net filtration, but also some adsorption, some chemical absorption to remove some of those things and protect us and give us that peace of mind. And then separate from the kind of the health aspects, then water softeners, making that water kind of friendlier for us to use, so our appliances last longer, so we need to use less detergent. That's kind of helping, things, not nitrates, but detergents have phosphates, have also effects on the wastewater end of things. And then the other one I chose to add here, there's other things you could put here, is reverse osmosis. And separate and distinct from these others, reverse osmosis, I think the simplest way to describe this is it's selectively isolating for water. Everything else is trying to take something out of water. This is trying to take water out of, and when I say that, it's trying to take the H2O out of the bulk bottle, right, out of the bulk material. It's selectively isolating water. That's a simplified way to look at it. I made the note, whatever, I'm not trying to compare dollar for dollar, but if you're talking about a water softener or a home filter, reverse osmosis is going to cost you some money. It also removes beneficial minerals, the calcium and the magnesium, the fluoride, all of those things. Like in simple terms, the only thing coming out of reverse osmosis is H2O. But again, that means your fluoride that was beneficial is gone. That means that the minerals that I grew up on a farm, right? I'm a farm kid. I like straight out of the well kind of water. It has a taste, and it has some of that taste because of the minerals. I get a bottle of water and it's reverse osmosis. Well, okay, it's not got nasty stuff in it, but it also doesn't taste, to my personal tongue, it doesn't taste very good. So, how much work am I going to go to? I'm going to go through reverse osmosis, then I'm going to remineralize it and try to, all of this stuff is stuff that we make prudential judgments on individually and collectively. Can you go back?
Yeah, sorry, go ahead.
Yeah, sorry. It's not only about us, it's also about our environment. It's about the other organisms that live in that environment. It's about humans that will follow us. So our individual choices add up. In Omaha, we have an organization called Under the Sink. It's not the place, but it's a place that I wanted to include here when you think about disposing things. I've got extra paint, I've got extra wax stripper from my floor, I've got something I used in my car. There's stuff that ought not go in our trash, because once in our trash, probably going to a landfill, and there's a possibility that it's interacting with our groundwater. So properly disposing of things is really, really, really important. Sometimes we're spreading them around intentionally. Things in our yard, in our gardens, the soap that we wash our cars with, the soap that we wash our laundry with, that goes into treatment. Laundry doesn't run off your yard, but we're making individual choices there as well. One of the things that I think is increasingly getting attention and is promoted, native plants. My wife and I, we had elm trees and they got decimated by the emerald elm beetle. And so we wanted to replace it with something. And so when we were looking at trees, we're like, hey, what would grow well here, right? It's these native plants. So we chose a redbud that's native to eastern Nebraska. I still have a bluegrass kind of lawn, and it looks better when it's treated the way bluegrass likes to be treated. But I grew up on a farm, and I know what native grasses look like and the beauty of native grasses and how those are suited to the climate where we're at. And so we can make individual choices on plantings and the chemicals that we're using and the environment in which those are growing. Those are all super important as well. That's me trying to cram a lot into more time than I intended to, but I want to make sure that we have time for any remaining questions and answers.
Yeah, we have a few.
Make sure you launch the survey.
Okay. Okay. Yeah, I think we have like 6 questions. So we'll go first with these two. From Jess, she asked, have we determined or have you seen evidence that increased energy needs, manufacturing, and hyperscale data centers are consistently affecting surface and groundwater? And is it widespread or targeted?
So it's a fantastic question, and I don't know the answer, but it is something that I'm thinking, like you are, more and more about. I think where I kind of approach that question is not so much on a, hey, here's this new thing, and there's going to be these new outcomes, and it's kind of sudden and a big change. Again, for myself, it's a little bit more of a continuum. because we've had all manner of industries, whether that's electrical production or some kind of manufacturing, or agriculture, right? All of these uses, all of these industries have water demands, and especially if heating and cooling is involved, there's usually a water load that's involved. So yes, I think we're right to pay attention. Yes, I think it's right that we use the water wisely. I'm not very Pollyanna about that yet, about the data center and this sort of stuff. We got to pay attention. And I think in particular, where I would encourage us to pay attention is how these things are being regulated and what kind of tax breaks and incentives and what kind of arrangements are being made. And none of those things are necessarily good or bad, but they have consequences, sometimes that are anticipated and oftentimes that aren't. And so that's the other thing that's difficult about some of that is oftentimes it's the unintended consequences that are some of the more impactful. So it's our job individually, collectively, to do the best that we can and then clean up when we made it oops.
All right, and then do you see focus in technology innovation in the water space, and is Nebraska well positioned to lead in this water space?
I think yes, and I think Nebraska is in a good place. We have outstanding colleagues at the university, both here in Omaha and in Lincoln. That includes chemists, engineers, physicians, and social workers. It's a whole network because there's so little that's not tied to water. Because we need it to be available to those industries. We need it to be available to agriculture. We need it to be available to recreation and then to everyday consumption and end users. I can think of a number of private entities in the area that to me are great resources for analyzing, monitoring water. It's not only the universities, it's the state as well. I see a lot of good things happening there.
All right, and then regarding the students doing the service learning, are these students chemistry students or non-STEM majors?
So I appreciate the question. In this particular case, so these were students in you might think of it kind of like a chemistry 101. It'd be like a first semester. Some of them, sometimes it was a second semester chemistry course. This is the chemistry course that we ask our science majors to take. It's also a course that non-science majors take. If you're curious, when I ask my students in that first semester course, about 70% of them have a health career in mind. And by the time they get to the second semester course, about 90% of them have a health career in mind. And so one of the motivating reasons for me in doing those service learning projects is not only so that they have a greater understanding and experience with the chemistry, but I want them to have that experience and understanding because I know where they're going, and they are probably unlikely to measure the calcium in a sample from some lake or river as a healthcare provider, but having that experience and knowing that the environment and where these people live and how they interact with water is an important factor to that person's health. And so those are important things to me. Did I get to the question, the heart of the question, Ava?
Yeah, she also kind of asked though, like what are the most effective ways for teaching scientific literacy, and if you have to like spend a lot of time demystifying and teaching scientific literacy before you're
Yeah, so that's another great question. So I've been teaching, those two courses and others for 25 years now. I just got my 25-year little award from the university, which I'm thankful for. I'm thankful to be here doing what I'm doing. I'll try to swing back to Ava. You have to remind me, but what I want to say is that I do what I do because the students I'm working with, they're going to do far greater things than I will, and I'm trying to help them on their way to doing those great things. I often use the example of, hey, somebody who's lost their sight or they were born blind. We don't, to the best of my knowledge, yet have the ability to restore sight for somebody, right? That would be fantastic if we could. Maybe it won't be one of my students, but I hope somebody someday, right? Like there are great things that can be done. So teaching for me is a fantastic way that I can support others doing good work. Read me the question one more time.
I think you kind of got to most of it, but I guess the only thing was like if you spend a lot of time demystifying it, or if
yes. So yeah, I'm gonna say that in over those 25 years, right, the evolution of my thinking and my teaching. When I first started, I like science, right, and I think science is cool, and understanding protons and neutrons and electrons and nitrates and partial charges and all the great chemistry, attraction, and these sorts of things. I think that's all very fascinating, and it's all very important to what we're trying to help students understand. What's changed for me is I refer to all those as the whats. Like our students need to know the whats, but they need to know the so whats and the now whats, and things like service learning and applications and case studies and those sorts of things help students. Help me to help the students to go beyond, oh, well, that's just 2 + 2, but to why do I care, I've done this long calculation, or I've arranged these things in a particular way. Why do I care, right? That's really, really important for students and allows them to understand why it matters, right? So.
Perfect. We just have one more pretty simple one. Karen wanted you to clarify that if you have hard water and are not using a softener, do the deposits help prevent lead leaking from the pipes? And then also she asked if you had a recommended filtration system.
Oh, good questions. So I can't speak to anybody's individual home. It's going to depend on the age of your home. So right, once upon a time, I talked about buying a water filter because I was now responsible for another small adult. Later on, I was responsible for a home. I became a homeowner, right? And so through that experience, I know that when you buy a home, depending upon the age of your home, you're going to sign off on this, that, or the other thing, demonstrating by your signature, your awareness that your structure might have lead-based paint, or your structure might have lead solder because of what technologies were in use or not at the time that you bought your home. So lead service lines are supplying the water from the utility to your home. I don't know, the majority of homes now have copper lines or galvanized. I remember the farm I grew up on had galvanized steel lines. Those are less common. And I remember my parents removing a lot of those and replacing them with copper. But you've got to know what's in your home. You've got to know what's in your water lines, right? To know at an individual level what's going to matter for you. The water softener is going to be downstream from those lead service lines. And so soft water and lead service lines, that's not to the best of my knowledge, not an area of kind of conflicting chemical behavior. Sound all right?
Yeah.
Okay, all right. Other questions from those present here? Yeah.
I have a few.
Okay.
Are they replacing any of the lead pipes, or I guess water pipes, with PVC?
That's a fantastic question. I have not paid as much attention to what they're using now. That said, when I walk around my neighborhood, I'm like, oh, they're digging over here, right? Looks like a new water line's going in. It looks. I didn't walk up to it and read the label, but it looks like, yeah, if you told me it was PVC, I would believe you. That's a really good question. I don't know, that would be an unsurprising material for that application, but I don't know if that's the exact material for that application or not. There's more than a few plastics out there. A lot of PVC pipe getting used in residential plumbing. There's other polymers being used now in residential plumbing. It's probably, with a whole lot of these things, it's one of those things where time will tell. We thought CFCs were pretty good for a long time. CFCs solved important problems, and I've left water quality. I'm on a different area of chemistry, right? But most of us these days don't. If I said CFC, that's not usually a positive connotation because we've since recognized that there's other issues that we did. And I don't think there's any way that we could have predicted that CFCs would have the negative impact that they did, right? In destroying the ozone layer. But we need to do what we can to be diligent, to check as well as we can as we're trying something new. And frankly, personally, I would advocate for the new thing, can we have it be as kind of natural as possible? Because some of the fancier stuff that we've come up with, even though it had some great function, a lot of times there were things that we didn't anticipate that did not serve us very well, right? I'll pause there. Otherwise, I'll have you here forever. You said you had several of them.
Yeah. So I guess, do you know if the federal government is looking to limit microplastics in pharmaceuticals?
Oh gosh, that's a great question. I am not as well tuned in terms of what the federal government is or is not kind of planning to do, but I somewhere in between us and the federal government are a whole collection of scientists. It is something that the scientific community is looking at, and that includes, both kind of folks at universities, be that public or private, or private industry or government organizations. It's yes, in a broad sense, they're paying attention to it. What they're planning to regulate or not regulate, and how and when, I couldn't tell you.
Yeah, and then because since they're not federally regulated right now, do you know if our water treatment plants in Omaha filter those out or have their own limit?
That's also a good question. I don't know the answer to that question, other than to say that they're part of that network of people paying attention. I expect they're trying to make the water as clean as possible, given that they're also trying to make it affordable. And it's not simply about economics, but there's definite, that's one of those big, economics is not something I think that we can easily get around, right? And so could they make it cleaner? Sure, right? We just pass all of it through reverse osmosis, but none of us want to pay that literal price, right? So, and frankly, that's probably cleaner than is really actually necessary. So what's the right level? And that's where we're making decisions, and we're trying, generally speaking, I think, to make the right decisions, to make good decisions, but we can also have a lot of dialogue about and potential disagreements about what we think is the right / good decision at any one of those stages. So we're trying, right? And we need to be trying, and we need to get it right, because the worst thing, particularly when I think about lead poisoning, I didn't include this graph, but I often will if I'm talking about lead poisoning, and that might occur through water, but there's a lot of other sorts of exposure that can lead someone to have lead poisoning. But if you look at a population level, some of the greatest instances of lead poisoning occur for infants. And they haven't the ability or the knowledge to protect themselves. And the exposure that they have at that age will impact them for a lifetime. And that's what's particularly sad, right? If I get lead poisoning, I'm not healthy. If my infant gets lead poisoning, it's an entirely different story. So it does, it matters. Others? Yeah.
So did you know that Iowa has the second highest cancer rates in the country?
What is Nebraska number 1 or are we number 3 or like it's?
No, I don't think Nebraska's like.
Okay. Okay.
But Kentucky's not.
Kentucky's number 1, Iowa's number 2. I think I heard that somewhere. You know.
My question is more like, would it be something in the water, or do you think it would be something?
I think water is an important place to look. No, I don't know. I don't know the answer. You know, I would want to know, you know, what makes Iowa different. What's different about the culture? What's different about the industry? What's different about the geology? What's different about the water, soil, air composition? Again, the toxicity of the things that they're exposed to aren't different from what they are in Nebraska. It's if I go back, can you go back, Ava, sorry?
Yes.
If you go back here, mostly I'm thinking about exposure and concentration, right? And those two things are related, but they're not the same thing. What's different about the exposure? What's different about the concentration in Iowa, in this case, in this question, as compared to somewhere else? If I change that up a little bit, I think Nebraska is number 1 for cancers related to radon. Like Nebraska is kind of number 1 for radon. Well, there's a reason for that, and it's because of our geology, right? And therefore, you know, we need to, in Nebraska, pay particular attention to our exposure to radon. And radon's not in our water, by the way. Radon's in the air. But just thinking about exposure, thinking about how those regional distinctions come to be, right? It's not because it's more toxic here or less toxic there. It's almost certainly more about exposure and concentration. It's a good question. Anything else?
I don't see anything on the Zoom here. Oh, wait. Oh.
Because I say, otherwise, you all know now that I provide long answers, and I appreciate the opportunity to share. I hope this has been helpful. If it generated more questions than answers, I'm going to call that a win, because that means you're thinking about it. And if there's something that I find valuable, it's stimulating the thinking of others. We've got to think about it more. We've got to think about it better. We've got to think about it together. Got to stop ignoring and burying our head and pretending X, Y, and Z, right? Like, we need to be engaged. So appreciate you being here. Appreciate you engaging today. And when you have those questions, it's pretty easy to find me through the university's website. You can email me, you can call me. If it's a government question, you should look up your senator or, you know, representative, whatever the case is. Look for those people that can impact you where you're putting your energy in. And you know, all those choices we make, part of those choices are where we're going to put our energy, because we can't do everything, right? So that's part of the reason also why I love teaching, because I've got a whole team of people that are joining our society, working on this, that, and the other thing, hopefully, so that we have good lives, right? That's kind of one of those Nebraska things, right? So thanks again, Ava, for helping to make this possible. Thanks for coming today in person. And for those of you who are on Zoom, I wish you well, and thanks for coming.
Yeah, I just have a few more things. Thank you all for coming. If you haven't gotten a chance to fill out the survey that was launched on the Zoom, I'll reiterate how we would greatly appreciate it if you took the time to fill it out. And if you want to share this with someone who wasn't able to attend tonight, or if you want to watch it again, the webinar will be posted on our YouTube, and that's the same for you guys, in the near future with all our past webinars. So yeah, thank you guys for coming in person. Thank you guys for coming on the Zoom and supporting conservation efforts. And most importantly, thank you to Dr. Dana Richter-Egger for this presentation, for sharing your time and talent. Have a great rest of your day.